Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Confidential computing is the discipline and set of technologies that protect data while it is being processed, placing strong isolation around computation, so sensitive information remains encrypted not only at rest and in transit, but also during execution. At the core are hardware-backed secure execution environments, often called enclaves or trusted execution environments, TEEs, which give code a protected memory region inaccessible to other software, hypervisors, or even some privileged system operators. In practice, confidential computing changes the trust assumptions of a platform. Instead of trusting every layer of the stack, you require cryptographic attestation that the code and its environment are genuine before any sensitive inputs are released to the enclave. For organizations working with regulated material, intellectual property, or multi-tenant workloads, confidential computing becomes a technical foundation for arguing that processing occurred under provable, tamper-resistant conditions rather than behind opaque administrative controls. The technological need for confidential computing is driven by a simple gap in traditional protections. Encryption protects data at rest and in flight, but while data is being used during model training, gradient aggregation, or inference, the plain text often appears in memory where it becomes vulnerable to insiders, compromised hosts, or side-channel attacks. This in-use window is particularly concerning for AI workloads, because models may process personally identifiable information, proprietary corpora, or sensitive business context that must not leak to cloud operators, other tenants, or adversaries who gain low-level access. Confidential computing reduces operational exposure by shrinking the trust perimeter and creating cryptographic proofs about the runtime. It is also a practical control against insider misuse. If only attested code inside an enclave can decrypt training shards, then casual or malicious access to the host no longer yields readable data, changing the economics of exfiltration and making audits more convincing to regulators and partners. Trusted execution environments, TEEs, are the hardware and microcode innovations that make confidential computing feasible at scale. TEEs provide memory isolation, enforceable access control at the CPU level, and mechanisms for attestation cryptographic assertions that a particular enclave is running a specific binary with an expected configuration. Major cloud providers and chip vendors offer TEE-backed services, from confidential VMs to specialized enclave runtimes, that integrate attestation flows and lifecycle controls into the platform. For AI workloads, TEEs can be used in a variety of ways: ephemeral enclaves for secure pre-processing of sensitive inputs, isolated training steps that perform gradient computations on masked data, or inference gates that decrypt prompts only inside an attested environment. These patterns allow organizations to demonstrate that sensitive operations occurred under audited, verifiable conditions, rather than leaving trust to contractual promises alone. Applying confidential computing to model training changes both threat modeling and operational practice. Instead of moving raw datasets into a shared cluster where many tools and operators can touch them, you can partition training into enclave-bound stages where data is decrypted, transformed, and contributed to gradient updates without exposing plaintext to the broader environment. Secure aggregation techniques can combine encrypted updates from multiple enclaves so the central coordinator sees only masked or aggregated gradients, reducing the risk of memorized sensitive data ending up in model weights. This approach supports audit-ready assurance. Attestation logs, signed checkpoints, and enrollment transcripts provide a chain of custody you can show to auditors or partners. Practically, teams must design training pipelines that accept enclave constraints, memory limits, I/O patterns, and orchestration semantics, yet yield models whose provenance and handling are demonstrably controlled. In inference and multi-tenant services, confidential computing protects prompts, business context, and sensitive responses by ensuring only attested, immutable code can access decrypted inputs and produce outputs. Confidential inference means prompts can be handled inside an enclave that enforces policy checks, redaction, and provenance marking before releasing any generated text to external consumers, which is valuable for regulated sectors, or when customers demand cryptographic guarantees about how their queries were processed. Attestation mechanisms provide cryptographic evidence-signed attestations and certificates that callers can verify independently, forming the basis for trust between parties that do not fully trust the hosting provider. The chain of trust extends from firmware and bootloaders through OS images to enclave binaries. Systematic attestation and measurement make tampering detectable and raise the bar for attackers who might otherwise manipulate model execution or substitute compromised code. Key management is central to confidential computing because secrets model keys, decryption keys for datasets, and signing keys for attestations must remain protected both in storage and inside enclaves. Enclave-specific key storage confines keys to protected memory and hardware-backed stores, while integration with hardware security modules, HSMs, or cloud KMS services enables rotation, revocation, and centralized policy control without exposing raw key material to host software. Operational patterns include ephemeral keys provisioned per session, short-lived certificates tied to attested measurements, and layered logging that records key usage without leaking the keys themselves. Audit logging is part of the design. Attestations, key usage events, and signed checkpoints create an evidentiary trail for compliance and incident response. Teams must plan key rotation and revocation workflows that tolerate enclave restarts, orchestration failures, and cross-region replication without creating windows where keys are unusable or exposed. Confidential computing imposes measurable performance considerations you must plan for, because isolation and hardware-enforced protection come at a cost that shows up in latency, throughput, and resource constraints. Enclaves typically reduce the amount of usable memory and can increase context switching overhead as data is marshaled into protected regions. This matters for large batch training and for wide transformer-based inference that expects abundant RAM. Scaling is not merely horizontal. Orchestration must consider enclave lifecycle, warm-up costs, and the limits of attestation services that gate session establishment. Workload tuning becomes an engineering discipline. Partition training into enclave-friendly stages. Use secure aggregation to reduce per-enclave state. Batch inference where acceptable. And design hybrid pipelines that keep heavy pre-processing outside enclaves while limiting plaintext exposure. Benchmarking under representative operational conditions is essential. Measure end-to-end latency, variance under load, and cost per useful prediction, so you can trade off confidentiality against responsiveness in a reasoned, documented way rather than by intuition alone. Confidential computing directly mitigates several high-risk threats that ordinary encryption and perimeter controls leave exposed, shifting the threat model in a way that benefits both security and compliance. Insider access misuse becomes materially harder because decryption keys and sensitive plaintext reside only in enclave memory that cannot be trivially dumped by administrators or operators. Attested binaries assert what code can access these secrets. Memory scraping and cold boot style attacks are contained because sealed memory regions and hardware protections reduce the useful residual data available to low-level compromises. Even hypervisor-level threats are reduced, if properly implemented, because enclaves minimize what the hypervisor can observe, though the architecture must still account for sophisticated side-channel efforts. Importantly, confidential computing raises the bar rather than promises invulnerability. You still plan for side-channel mitigation, supply chain risk, and post-quantum key lifecycle, but you do so against a platform where high-confidence attestation and limited plaintext windows change the attacker's calculus. There are several deployment models for confidential computing, and each presents different operational trade-offs you should weigh against legal, cost, and integration constraints. Cloud provider offerings, confidential VMs, and managed enclave services provide convenience and scale with provider-attested root of trust and integrated key management, but they often tie you into vendor ecosystems and require rigorous legal evaluation about jurisdiction and access. Containerized enclaves let you package workloads more flexibly while retaining enclave protections, useful for hybrid orchestration and microservices patterns. They demand orchestration layers that understand attestation and image signing. Hybrid architectures combine on-premise enclaves for the most sensitive operations with cloud enclaves for elasticity, enabling a data residency or regulatory split while complicating orchestration and audit collection. On-premise hardware affords maximal control over the supply chain and physical access, but increases capital and operational overhead. Choose a model by mapping sensitivity, scale, and sovereignty requirements to the deployment surface you can sustain. Integrating confidential computing into AI pipelines is a practical engineering challenge that requires rethinking several standard practices so evidence, performance, and governance align. For training, design confidential clusters where data shards are decrypted only inside attested workers and where secure aggregation merges gradients without exposing individual contributions. Sign and version checkpoints so you can tie each model artifact to an attested lineage. For inference, wrap prompt handling and policy enforcement inside enclave gates that produce signed attestations of the steps taken and the artifacts used, enabling downstream consumers to verify provenance and compliance. Enclave-based plugin execution offers a model for third-party code, allow vendors to run only within attested sandboxes, and require signed interfaces and evidence export for any external tool call. The orchestration layer must capture attestation logs, signed checkpoints, and key usage events into tamper-evident audit stores, integrating with CI/CD, so model promotion depends on passing enclave-ready gates, and so reruns reproduce attested states for auditors and incident responders. The strategic benefits of adopting confidential computing extend beyond technical controls into customer trust, competitive differentiation, and jurisdictional readiness. By demonstrating you can process regulated or sensitive data within provable enclaves, you make possible collaborations, data-sharing consortia, cross-company training, or hosted inference for sensitive clients that were previously blocked by governance or trust gaps. Confidential runtimes provide concrete evidence for compliance teams and auditors. Attestation records, signed checkpoints, and sealed logs are credible artifacts that can reduce friction in procurement and partnership negotiations. Reducing insider risk and technical access windows also lowers the insurance and legal tail risk associated with high-value datasets. In highly regulated sectors healthcare, finance, defense, confidential computing can be the enabler that turns a risky proof of concept into a revenue-bearing product with clear demonstration of controlled processing, improving both market access and stakeholder confidence. Limitations of confidential computing are real, and you should quantify them with metrics so discussions about adoption are informed rather than ideological. Hardware availability and vendor support vary by region and cloud, creating constraints on where workloads can run. Integration complexity raises engineering debt as orchestration, key management, and attestation must interoperate across stacks. Performance overhead. The extra latency and reduced memory available in enclaves should be tracked as a percentage cost against throughput and a direct input into capacity planning. Relying on vendor ecosystems introduces lock-in risk, so measure coverage of workloads that can fit into enclave constraints and maintain contingency plans for non-supported cases. Cost overhead is not just per-hour compute, it includes specialized tooling, auditing, and sourcing of attested images. Define effectiveness metrics: attestation success rate, percentage of sensitive workloads processed confidentially, incident reduction attributable to in-use protections, and use those numbers to justify scope, budget, and the phased rollout of confidential computing capabilities. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Measure the effectiveness of confidential computing with metrics that map technical assurance to operational impact. Because leaders will fund what you can prove, and auditors will question what you cannot demonstrate. Start with attestation success rate, the proportion of enclave sessions that complete attestation and operate within expected measurements. which directly indicates how reliably your platform proves its trusted state to callers and partners. Track performance overhead as a percentage of baseline latency and cost per inference or cost per training step so you can balance confidentiality with responsiveness and budget, and correlate those figures with adoption rates and pilot cohorts. Measure workload coverage, the fraction of sensitive datasets, model checkpoints, and inference sessions that the program processes under enclave protection versus those still handled in conventional environments. Finally, attribute incident reduction by comparing the frequency and severity of insider or host-level exposures before and after confidential deployment. These outcome-based metrics convert technology into risk reduction stories that executives, auditors, and customers can evaluate with confidence. As you adopt confidential computing, assemble a tooling ecosystem that turns architecturally promising ideas into reproducible engineering practice rather than artisanal projects. Enclave SDK's libraries that simplify careful memory handling, secure I/O, and attestation APIs reduce developer friction and lower the chance of subtle implementation flaws that defeat the whole point of the hardware. Confidential VM and managed enclave services provide integrated attestation flows, KMS hookups, and lifecycle controls, but you should wrap them in your own orchestration and CI/CD, so signed images, policy artifacts, and attestation logs become first-class artifacts in release pipelines. Cloud-native attestation tools and monitoring dashboards translate raw attestations and key usage events into searchable evidence for incident response and compliance. Prioritize tools that export reproducible tamper-evident logs and that integrate with HSMs or your centralized key vault so you do not rely on ad hoc scripts in a crisis. In short, aim for a composable stack SDKs, attestation orchestration, key management, and audit stores that operationalizes confidentiality across the model lifecycle. Confidential computing intersects directly with compliance regimes in ways that both simplify and complicate audits, so treat regulatory mapping as a design input rather than a later translation exercise. Map attestations and signed checkpoints to specific legal obligations, data residency proofs, consent boundaries, or controls required by health and financial rules. Where laws demand demonstrable measures to protect data in use, attestation logs and enclave-protected processing become potent evidence, often more convincing than procedural attestations, because they show cryptographic proof of runtime state and limited exposure windows. Yet compliance requires more than attestations. Preserved audit trails, accessible evidence packages, and clear narratives linking attestation to policy are essential for regulators to accept technical assurances. Prepare curated evidence bundles, signed measures, key lifecycle records, and model provenance that compliance and legal teams can present, and document the conditions under which enclaves were used so review processes are efficient and defensible. Resilience practices for confidential computing ensure that protected execution is not an operational Achilles. Heal when failures occur. Design for graceful degradation, redundancy, and recovery from attestation or hardware faults. Implement fallback strategies that maintain confidentiality posture. For example, if attestation services falter, block plain text release and queue encrypted artifacts for deferred processing rather than defaulting to an unprotected execution path. Architect redundancy across availability zones and diverse hardware stacks, so enclave failures in a single vendor or region do not halt critical workflows. Periodic attestation checks should be scheduled and logged so you detect drift changes in firmware or measurement that could undermine trust, and you must define rapid rotation and revocation paths for keys and images when compromise is suspected. Finally, exercise these practices through chaos and recovery drills so teams prove they can rotate keys, reprovision enclaves, and restore attested states without losing data or extended downtime. Resilience is demonstrated by rehearsed recovery, not by optimistic diagrams in slide decks. Strategically, confidential computing becomes an enabler of partnerships, market access, and risk transfer when you align technical capability with business questions customers actually ask. Many partners want to collaborate on sensitive training data but cannot accept blanket administrative access to hosts. Attested enclaves and sealed processing change that negotiation by offering cryptographic guarantees about what happened to the data. For regulated customers, confidential runtimes reduce procurement friction because they materially lower the chance that a cloud operator or shared host could read protected inputs. This capability can open new commercial avenues: data cleanrooms, cross-organization training consortia, and hosted confidential inference for high-value clients, while also shifting insurance and contractual risk calculations. However, realize that customers will need education. Describe what enclaves protect, what they do not, side channels, supply chain risks, and what evidence you will provide. Framed honestly, confidential computing strengthens trust and expands opportunity. Framed as marketing without substance, it invites skepticism. Concluding a practical adoption plan. Prioritize pilots that demonstrate end-to-end confidentiality value rather than isolated technical proofs, because organizations fund demonstrated risk reduction more readily than theoretical capabilities. Choose pilot cases where the sensitivity and scale of data justify enclave constraints, narrow clinical datasets, high-value proprietary inputs, or partner-shared corpora so outcomes are meaningful and measurable. Instrument every pilot with the metrics above, bake attestation and key management into CI/CD, and prepare audit-ready evidence bundles from day one. Use lessons from pilots to refine runbooks, estimate costs, and adjust the product roadmap. If latency is unacceptable, redesign the split between inside and outside enclave work. If attestation fails unpredictably, deepen orchestration and hardware inventory controls. Over time, migrate higher value and higher risk workloads into confidential pipelines, documenting residual cases where enclaves are impractical and compensating with layered controls. This phased, measured path turns confidential computing from a technical experiment into a durable capability that supports sensitive AI use while keeping governance, performance, and cost in balance. No technology is a panacea, and confidential computing arrives with concrete limits you must acknowledge when designing programs. Hardware availability varies by region and cloud provider, producing uneven coverage that constrains where workloads can run. A global deployment often requires hybrid architectures and careful jurisdictional mapping. Integration complexity is substantial. Attestation, key management, orchestration, and audit stores must interoperate across CI/CD, HSMs, and identity systems, creating engineering debt unless you invest in repeatable patterns and automation. Vendor ecosystems introduce lock-in risk and legal nuance: whose attestation keys, what subpoena powers exist, and which supply chain assurances are verifiable. Performance overhead matters practically, not rhetorically. Enclaves reduce usable memory and add latency, forcing trade-offs between confidentiality and responsiveness. Finally, confidential computing raises rather than eliminates some threat-side channels. Physical hardware compromise and supply chain insertion remain real concerns. So you should treat the technology as a major risk reduction measure that must be combined with other defenses rather than as a silver bullet. Measuring whether confidential computing actually moves the risk needle requires a mix of technical indicators and business-oriented outcomes that you can present to leaders. Start with attestation success rate to show how reliably enclaves complete trusted handshakes, and track performance overhead as a percentage of baseline latency and cost per inference so you quantify operational trade-offs. Coverage of workloads tells you what fraction of sensitive training shards, inference sessions, or partner integrations actually run under enclave protection. This helps prioritize future migration. Incident reduction metrics, fewer host-level exposures, or reduced severity of data-in-use incidents are the outcome measures executives care about, but they should be correlated to enclave adoption rather than assumed causal. Finally, measure audit readiness. How often can you produce time-stamped attestation logs, signed checkpoints, and key usage records within SLA windows? Numbers that map to procurement, compliance, and insurance conversations make the business case for continued investment. Turning technology into repeatable practice depends on a coherent tooling ecosystem and disciplined engineering patterns that lower developer friction and preserve evidence. Enclave SDKs are the first order of business. They hide the memory safety and marshalling details so application code can decrypt and process without subtle bugs. Managed confidential VM and enclave services provide integrated attestation and KMS connections, but you must wrap them in your own orchestration to ensure signed images, attestation logs, and policy artifacts flow into CI/CD and audit stores. Monitoring tools that understand attestation semantics and key events turn raw attestations into actionable alerts and searchable evidence. Prefer dashboards that correlate attestation failures with key rotation issues, image provenance mismatches, or unusual enclave life cycles. Integration with HSMs, centralized key vaults, and policy-as-code systems ensures key rotation, revocation, and signed release processes are automated and auditable. Choose components that export tamper-evident logs and support reproducible builds, so incident response and regulatory reviews are practical. Confidential computing maps to compliance in ways that can materially reduce friction with regulators if you prepare evidence correctly. Many data protection regimes focus on access and control. Attestations and sealed processing logs provide cryptographic proof that plain text existed only briefly and only within a measured runtime, which is persuasive to auditors and partners. However, you must package evidence thoughtfully. Signed attestations, checkpoint provenance, and key rotation records need narratives that explain what was processed, why, and under what legal basis. Certification regimes and sector-specific standards may recognize enclave-based controls differently. Map your attestations to the clauses regulators expect: data residency, breach notification, or contractual confidentiality obligations, and prepare extraction scripts that compile audit bundles on demand. Remember that technical proofs supplement but do not replace legal obligations. Counsel and compliance must co-author the evidence templates you present. Operational resilience is critical, because confidential computing can become an Achilles heel if attestation or hardware failure halts critical paths. Design fallback behaviors that prefer safe denial over risky default. If attestation services are unavailable, queue sensitive operations for deferred attested processing, or fall back to conservative policy-enforced modes rather than running unprotected. Build redundancy with attested instances across regions and vendors, so hardware faults or vendor outages do not silence protected workloads. Periodic attestation checks continuous measurement of firmware, enclave images, and boot chains detect drift and hardware changes that could erode trust, and you must have rapid revocation and rotation procedures for keys and images when suspicion arises. Exercise recovery in rehearsed drills. Rotate keys, reprovision enclaves, and restore attested states to validate runbooks. Resilience is operational proof that confidentiality remains meaningful even when parts of the system fail. Strategically, confidential computing is a high-leverage capability for organizations that handle sensitive data, operate in regulated sectors, or seek partner trust for joint modeling efforts. It expands possibilities: data clean rooms with provable processing, hosted inference for clients who refuse administrative access, and cross-organization learning that preserves each party's privacy. Yet adoption should be pragmatic. Pilot meaningful workloads, instrument outcomes, and build the orchestration and legal narratives that turn cryptographic attestations into contractual assurances. Treat confidential computing as part of a layered security architecture, paired with provenance, watermarking, robust governance, and strong key hygiene, so it amplifies, not replaces, existing controls. As you adopt these practices, prepare for the next challenge in adversarial automation: systems that generate highly plausible synthetic artifacts at scale. The protections you build today, attested, auditable, and resilient, will be essential in defending against automated adversarial generation and sustaining trust in AI. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.